Hi, I'm Bob. Let's solve the problems from 1 to 6 at the end of Chapter 4, Multiple Regression Analysis, Inference. Let's look at the first problem. The t-statistics are valid if all the classical linear model assumptions are satisfied. There were 6 assumptions: linear in parameters, random sampling, no perfect collinearity, zero conditional mean, homoscedasticity, and normality. Under the 6 classical linear model assumptions, the t-statistics have t-distributions under the null hypothesis. In the first case, heteroscedasticity violates the homoscedasticity assumption. In the third case, omitting an important explanatory variable violates the zero conditional mean assumption. That is, if the error term is heteroscedastic or the error term is correlated with the explanatory variable, the t-statistics of the estimates no longer have the t-distribution under the null hypothesis. In the second case, when the two independent variables are highly correlated, the 6 classical linear model assumptions still hold. Therefore, the usual OLS t-statistics are valid unless the 2 independent variables are perfectly collinear. Let's do the second problem. Consider an equation to explain the salaries of CEOs in terms of annual firm sales, return on equity, and return on the firm's stock. The first question is about the null hypothesis. After controlling for sales and return on equity, the return on the firm's stock has no effect on the CEO's salary. The null hypothesis is that beta 3 equals 0. The alternative hypothesis is that better stock market performance increases a CEO's salary, that is, beta 3 is greater than 0. The second question is about the interpretation of estimates. If the return on the firm's stock increases by 50 percentage points, then 0.00024 times 50 equals 0.012 or 1.2%. The CEO's salary increases by 1.2%, holding sales and return on equity fixed. That is not a particular large effect on salary. We also find that the effect is not statistically significant at any conventional significance level. The t-statistics is 0.44. The third question is about testing against the one-sided alternative. From the t-distribution table, we find that the one-sided critical value at the 10% significance level with 204 degrees of freedom is 1.282. The t-statistic for the estimate of beta 3 is 0.44, which is smaller than the critical value. We could not reject the null hypothesis that the the return on the firm's stock has no effect on the CEO's salary, after controlling for the firm's sales and the return on equity at the 10% level, against a one-sided alternative. For the fourth question, I will include the return on the firm's stock in the model. First, we usually include explanatory variables in the model based on economic theory and common sense. The stock market performance should be a determinant of the CEO's salary. Second, the disadvantage of adding one more explanatory variable is that if it is highly correlated with another explanatory variable, then the standard errors will become larger, the t-statistics will become smaller, the confidence intervals will become wider, and the estimates will become inaccurate. When we look at the estimated equation, we find that the other two explanatory variables are still very statistically significant. It seems that including the return on the firm's stock does not harm the estimates of the other two explanatory variables in this example. Third, if it is left out of the model, it may lead to omitted variable bias of the estimates for the sales and the return on equity. Therefore, although the estimate for the return on stock is not significantly different from zero, I will still include it in the model. Let's find the answer to the third problem. The first question is about the interpretation of the estimate on sales. If sales increases by 10%, the expenditures on research and development are estimated to increase by 3.21 percentage points, which is 0.321 times 0.1 equals to 0.0321 or 3.21 percentage points. It's not an economically large effect, but also not trivial. The second question is about the t-test against a one-sided alternative. The null hypothesis is beta equals 0, and the alternative hypothesis is beta is greater than 0. The t-statistic is 1.486. The one-sided 5% critical value for a t-distribution with 29 degrees of freedom is 1.699. Since the t-statistic is smaller than the critical value, we fail to reject the null hypothesis at the 5% level against a one-sided alternative. The one-sided 10% critical value with 29 degrees of freedom is 1.311. Since the t-statistic is greater than the critical value, we reject the null hypothesis in favor of the alternative at the 10% significance level. In other words, R&D intensity increases with sales at the 10% level. The third question is to interpret the coefficient on the profit variable. As the profit-sales ratio increases by 1 percentage point, the R&D sales ratio increases by 0.05 percentage points. That is, if the profit-sales ratio increases by 10 percentage points, the expenditures on R&D increase by 0.5 percentage points. It is not an economically large effect. For the last question, the effect is not statistically significant at any conventional level, with a t-statistic of 1.087. For example, the one-sided 10% critical value with 29 degrees of freedom is 1.311. The two-sided 10% critical value with 29 degrees of freedom is 1.699. The t-statistic is below these critical values. We fail to reject the null hypothesis that the profit-sales ratio has no effect on the R&D expenditures. Let's go to the fourth problem. For the first question, the null hypothesis is that beta 3 equals 0. The alternative hypothesis is that beta 3 is not equal to 0. The second question is about the signs of the parameters. I expect beta 1 and beta 2 to be positive. A higher city population implies a higher demand for housing, which will drive rents up. So beta 1 should be positive. A higher average income implies a higher opportunity cost of building houses, leading to an increase in rent. So beta 2 should be positive. The third question is about the interpretation of coefficients on a log-log model. The coefficient on the log population is an elasticity. If the city population increases by 1%, the rental rates will increase by 0.066% on average, holding other factors fixed. So a 10% increase in population is associated with a 0.66% increase in rent. The fourth question is to do the t-test. The t-statistic is 3.294. The two-sided 1% critical value with 60 degrees of freedom is 2.660. The t-statistic is above the critical value. So we reject the null hypothesis in favor of the alternative at the 1% level. The effect is statistically different from 0. If the size of students relative to the total population increases by 10 percentage points, the rent will increase by 5.6% on average, holding other factors fixed. Let's go to the fifth problem. The first question is about the confidence interval. We use the formula to construct the confidence interval for the beta. The constant C is the critical value. The two-sided 5% critical value with 137 degrees of freedom is 1.960. The lower and the upper bounds of the confidence interval are 0.228 and 0.596, respectively. So the 95% confidence interval is from 0.228 to 0.596. For the second question, we could not reject the null hypothesis at the 5% significance level because 0.4 is inside the 95% confidence interval. We can also do the t-test, compute the t-statistic, and compare it with the critical value. The t-test is equivalent to the confidence interval method. In addition to the t-test and the confidence interval method, we could calculate the p-value for the estimate. In this question, the p-value is 0.9, which is evidence we could not reject the null hypothesis. For the third question, since the null hypothesis 1 is outside the confidence interval, we reject the null hypothesis against a two-sided alternative at the 5% significance level. We can also use the t-statistic or the p-value. Notice that the two-sided 5% significance level corresponds to the 95% confidence interval. Let's do problem number 6. The first question is about the significance test of the estimates. The null hypothesis is beta 0 equal to 0, and the two-sided alternative is beta 0 not equal to 0. The t-statistic is minus 0.889. We now have three ways to do the significance test. Using the p-value with 86 degrees of freedom, we have the p-value equal to 0.376. It suggests we could not reject the null hypothesis even at the 30% significance level. Using the critical value comparison, we find the two-sided 10% critical value with 86 degrees of freedom, which is 1.662. Since the absolute value of the t-statistic is smaller than the critical value, we fail to reject the null hypothesis that the intercept is 0. We could test beta 1 equal to 1 against the two-sided alternative. We calculate the t-statistic first. It is minus 0.490. We find the two-sided 10% critical value with 86 degrees of freedom, which is 1.662. Since the absolute value of the t-statistic is less than the critical value, we fail to reject the null hypothesis at the 10% level. We could also compute the p-value. It is 0.626. We have the same conclusion. We could not reject the null hypothesis even at the 60% significance level. The second question is about the F-test. The null hypothesis contains two exclusion restrictions. We use the sum of squared residuals form of the F statistic. The numerator is the sum of squared residuals from the restricted model minus the sum of squared residuals from the unrestricted model, and then divided by the number of restrictions. The denominator is the sum of squared residuals from the unrestricted or the original model, divided by the model's degrees of freedom. Plug in all the elements, and we have the F statistic equal to 11.38. From the F distribution table, we find that the 1% critical value with 2 and 86 degrees of freedom is 4.85. The F statistic is greater than the critical value, so we reject the null hypothesis at the 1% level. The third question is about the R-squared form of the F statistics. The long model is the unrestricted model and the short model is the restricted model. We have the R-squared for each model. The number of restriction is 3. The degrees of freedom in the unrestricted model is 88 minus 5, which is 83. We can calculate the F statistic, which equals 1.456. From the F distribution table, we find that the 10% critical value with 3 and 83 degrees of freedom is 2.15. The F statistic is smaller than the critical value, so we fail to reject the null hypothesis and conclude that lot size, square feet, and bedrooms are jointly statistically insignificant at the 10% level after controlling for SS. We can also find the p-value for the F test. It is 0.233. It means that these 3 explanatory variables are not jointly statistically significant even at the 20% level. The last question is about the validity of the F test. If all the classical linear model assumptions are satisfied, the F statistics have an F distribution under the null hypothesis. If the variance of price changes with the explanatory variables, the homoscedasticity assumption is violated. Therefore, the F test is no longer valid. Thank you for watching this video and subscribing to my YouTube channel. See you next time.